Welcome to the deep dive. We're here to, really get into the weeds on interesting topics and hopefully give you those moments where things just click. Today we're tackling something that honestly most of us probably do without a second thought. Static stretching. It's been drilled into us, hasn't it? Flexibility, injury prevention, even like boosting performance. But what if the science tells a slightly different tale, especially when it comes to really quick, powerful movements? So our goal today is to really unpack how even a pretty standard short static stretch, just 60 seconds, could be changing how our muscles fire and how we perform in explosive activities. We're going deep.
Exactly. And we're grounding this discussion in a really specific recent study. It's titled 60-Second Static Stretching of Lower Limb Muscles Disrupts Muscular Performance and Control in Active Male Adults. This is research by Weishuai, Youngsuk Kim, Junsig Wang, Tengfei Xuan Tang, and Sukwon Kim. You can find it in the Journal of Sports Science and Medicine, volume 24, pages 195 to 204, published in 2025. For anyone wanting to check it out themselves, the DOI is available online, and the timeline was pretty quick received, late 2024, published early 2025.
Okay, perfect. So let's get into it. Our mission for this deep dive.
Yeah.
Break down this study, figure out how they did it, what they found, and what 60 seconds of stretching actually does to, say, your squat jump power. Time to get properly informed.
Right. Well, first off, it's important to say static stretching is super common, has been for ages. It's sort of baked into how we think about getting ready for exercise, The idea it helps flexibility and stops injuries as well. It's pretty widespread.
Totally. I mean, I can still picture my coaches telling you to hold that quad stretch forever before games.
Longer felt better, right? But I guess the science has shifted.
It really has. Over the last, say, 25 years, there's been a growing body of research suggesting that holding static stretches for too long, especially right before you need strength or power, might actually work against you. People like Kay and Blazevich pointed out way back in 2012 that stretching for 60 seconds or more could potentially dial down muscle tension and something called neural drive.
Neural drive. Okay, break that down for us. Is that like the signal strength from the brain to the muscle? Like turning up the volume?
That's a really good way to think about it, yeah. It's the intensity of the electrical command telling your muscles, okay, contract, now. So if static stretching sort of dampens that signal, it's like asking your muscles to shout right after telling them to whisper. It's made people rethink warm-ups, definitely.
Makes sense. And that leads us right into the core ideas of this study. Neuromuscular control and muscle synergies. Muscle synergies. Sounds complex. What are they, in simple terms? Okay, imagine your brain is trying to conduct an orchestra with thousands of instruments, individual muscle fibers. Telling each one exactly what to do constantly would be overwhelming, right?
Chaos.
So the brain simplifies. It groups muscles that tend to work together into these synergies. Think of them like preset patterns or squads. The brain just activates a whole synergy, maybe adjusting the contribution, the weighting of each muscle within that group slightly to get a smooth, coordinated action, like walking or jumping.
Ah, okay. So instead of micromanaging every skill fiber, the brain uses these coordinated team plays.
Sure.
Why is that concept so key for understanding stretching's effects? What was the gap they wanted to fill?
It's crucial because these synergies are fundamental to moving effectively, efficiently, and even safely. They're surprisingly stable across different tasks. But here's the gap. Most older research looked at how stretching affected, say, one muscle's force output, or maybe that neural drive to one muscle. They hadn't really looked at how stretching messes with the coordination of these entire muscle teams during something complex and demanding like a squat jump. We knew about the players, not the teamwork.
Gotcha. So this study zoomed out to look at the whole orchestra, not just the first violin. And their specific guess, their hypothesis, was that stretching wouldn't change the number of teams playing.
Exactly. They predicted the number of synergy patterns would stay the same.
But it would change how much each player contributed to the team effort and when they kicked in. Subtle, but important.
Very. It shifts the focus from if muscles work together to how that teamwork changes after a stretch.
Okay, so how did they test this? They used a pretty smart design, a randomized crossover experiment. This means every participant did both the stretching session and the non-stretching session, acting as their own control. Really helps isolate the effect of the stretching itself. They had 25 active young men, average age around 22 and a half, all healthy, no lower limb injuries or neurological issues.
Right, clean slate.
Yep. And they had at least 24 hours between the two sessions, the static stretching SS1 and the non-stretching NS1 to avoid any carryover effects.
And the stretching itself, what did that involve? Just holding a stretch. It was specific, 60 seconds total, but cumulative for 3 key muscle groups in the lower leg. quads, hamstrings, and the calf muscles. The triceps surae, so how did they get to 60 seconds?
They did 2 reps of a 30-second hold for each muscle group on each leg, with a 15-second rest between holds.
Okay, and importantly, they stretched to discomfort, not pain. Then a 3-minute rest before the jump test. Exactly, that rest is important too. Then came the test, a squat jump, but a specific kind, the SJ 90 degrees. Participants stood, squatted down until their knees were at a 90-degree angle, held it for about a second.
Holding it there, that probably minimizes the bounce, right? The elastic effect.
Precisely. It reduces the contribution from stored elastic energy and stretch reflexes. They really wanted to isolate the muscle's voluntary power output. Then, from that 90-degree hold, they jumped vertically, as fast and hard as possible, hands held across the chest to stop arm swing influencing the jump height.
And they measured all this with some serious tech, I assume, not just eyeballs and a tape measure.
Oh, yeah.
High-tech setup, a 3D motion tracking system with 13 infrared cameras to map out the movement precisely. Plus, a force platform underfoot to measure the actual ground reaction forces the power of pushing off the ground.
And crucially, for the muscle synergies, they used electromyography EMG, sensors placed on the skin over 5 key leg muscles: biceps femoris, a hamstring; triceps surae, calf; rectus femoris, a quad; vastus lateralis, and vastus medialis, 2 other quad muscles, recording all the electrical chatter.
Wow, there's a ton of data flowing in. How do they make sense of all that muscle activity?
They used a mathematical technique called non-negative matrix factorization, NMF. It's pretty clever. It basically lets you take that complex mix of EMG signals and break it down into 2 main components. First, the underlying motor modules. Think of these as the stable, consistent patterns of muscle coactivation, the synergy blueprints. And second, the motor primitives. These are the time-varying activation signals that scale those blueprints, telling the muscles when and how intensely to fire during the jump.
Okay, so it separates the what muscles work together part from the when and how much they activate part.
Exactly. This allowed them to quantify each muscle's contribution within a synergy and pinpoint its activation timing. And doing this, they confirmed that consistently 2 main synergy patterns emerged during the squat jump, whether the participants had stretched or not.
All right, let's get to the juicy part, the results. What happened with those synergy patterns after stretching?
Well, just as they hypothesized, the number of muscle synergy patterns didn't significantly change. Whether they stretched or didn't stretch, the participants still used those same 2 fundamental coordination patterns for the jump. The basic team strategy remained intact, numerically speaking.
Okay, so the brain didn't suddenly invent a new way to jump. But did they jump as high? Ah, that's the kicker. No, they didn't. Jump heights were significantly lower after the 60 seconds of static stretching compared to when they didn't stretch. And it wasn't a tiny difference either. They reported a moderate effect size, meaning it was a noticeable performance drop. A minute of stretching made them jump less high.
Right, and this is where the synergy details get really interesting, because while the number of patterns stayed the same, how the muscles contributed within those patterns and when they activated definitely changed. For example, in one of the synergies, called Module 2, the overall contribution or weighting of the muscles involved was generally lower after stretching compared to no stretching.
So in that specific team play, the players were contributing less overall after stretching.
Kind of, yeah. A general dialing down within that specific synergy.
But wasn't there one muscle that did the opposite? This is the bit I found really surprising. I expected everything to be dampened.
You're right, that's the fascinating twist. In the other synergy, Module 1, something different happened. While most muscle contributions weren't significantly different, one specific muscle, the vastus medialis, or VM, one of the quad muscles, its weighting was significantly higher after stretching.
Higher, so it was working harder.
Substantially harder, yes. It was a large effect size. This completely goes against the simple idea that stretching just weakens everything. It suggests the body was compensating.
Compensating? Like, because other muscles were maybe underperforming due to the stretch, the VM had to step up and pull more weight.
That seems to be the interpretation, yes. Like one player suddenly having to cover more ground because teammates are a step slower.
And did the timing change, too, when these muscles fired?
Hugely. This was another major finding. Timing is critical for explosive power. In the early part of the jump's push-off phase, roughly the first 18% to 40%, the muscles in the non-stretched condition showed significantly higher activation levels, much stronger initial burst.
So without stretching, the muscles fired harder, sooner. Got it.
But after stretching, that initial burst was weaker. And then conversely, in the late phase of the jump near the end of push-off and into the flight phase, specifically for one of the activation signals, primitive 1, the stretched muscles, showed significantly higher activation levels.
Ah, so they were less active early on, but more active later, playing catch-up.
Exactly, trying to compensate for the weaker start. Again, a large effect size, so a big difference in timing.
Okay, let me try and summarize this for you, the listener. 60 seconds of stretching didn't change the number of muscle teams used for the jump, but it did mess with the team dynamics. Overall jump height went down, some muscles contributed less, one key muscle, the VM, contributed more, and the timing shifted weaker start, stronger finish. It's a complex reshuffle.
That's a great summary. It's not just inhibition, it's a reorganization, a less efficient one, apparently. So let's unpack the why. Why the VM compensation? Why the timing shift? The researchers suggest it comes down to that weaker start. The low activation levels early in the jump, likely due to the stretching reducing neural drive or maybe muscle stiffness slightly, force the body into this compensatory activation later on. It had to work harder in the later stages to try and salvage the jump height, even though the overall result was still lower performance.
Right, the body's trying its best to adapt. And this links straight back to that neural drive idea, doesn't it?
Yeah.
Less drive means a slower, weaker start.
Absolutely. The unstretched muscles likely maintain that higher neural drive, that quicker, stronger go signal, allowing for that powerful initial activation crucial for explosiveness. Stretching seems to blunt that initial edge, maybe affects the muscle's immediate springiness too, forcing this less optimal delayed activation strategy.
And the fact that the body can compensate is amazing, but it has consequences, right? Making one muscle, like the VM, work extra hard might not be ideal.
Probably not. It suggests a less efficient movement pattern. While the neuromuscular system is adaptable, forcing compensation like this could potentially increase strain on that specific muscle or just lead to poorer overall performance, certainly in that jump task. It's like your car engine sputtering initially and then revving high to catch up. Not smooth, not efficient.
And this study is really valuable because it's looking at the whole picture, the synergy, not just isolated parts.
Precisely. It's one of the first, if not the first, to really analyze static stretching's impact through this lens of multi-muscle coordination during a dynamic, powerful task. It fills a big gap.
Okay, so the big question, what does this mean for you listening? For athletes, coaches, gym goers, anyone who stretches, what's the practical takeaway?
Well, the study offers some pretty clear pointers for optimizing how we prepare for exercise. First, it really advises caution about prolonged static stretching, like this 60-second cumulative dose per muscle group right before activities needing high-intensity explosive power.
So, yeah, maybe holding that deep hamstring stretch for a minute right before sprinting or jumping isn't the best idea. Could actually slow you down or reduce your jump height.
That's what this data suggests, yes. So for athletes and coaches, maybe lean more towards dynamic warm-ups, things like leg swings, torso twists, high knees, butt kicks. Or if you do use static stretches, perhaps keep them much shorter right before explosive work. The goal is to get muscles ready to fire quickly and strongly from the get-go, avoiding that delayed start we saw.
Okay, that makes sense. Shift towards movement prep rather than just passive holding.
Yeah.
But what about flexibility? If someone feels genuinely tight?
That's a fair point. And it leads to the second takeaway. The need for potentially more personalized stretching programs. Remember how the VM compensated while others didn't? Stretching doesn't hit all muscles equally in terms of functional outcomes, so coaches, therapists maybe need to think about which muscles are being stretched for how long and when relative to the activity. A blanket stretch everything for 30 seconds might not be optimal, especially pre-performance. Maybe save the longer static holds for after training or on recovery days.
Right, tailoring it more. Don't just stretch everything the same way if the impact isn't uniform. What else?
The third point relates to what they call muscle activation homeostasis, basically, keeping things balanced. The unstretched muscles performed better, especially early on. This suggests that if you are doing static stretching, ensuring it's balanced across the relevant muscle groups might be important to avoid creating imbalances where some muscles are dampened more than others, leading to that inefficient compensation and performance drop.
Fascinating. Super practical insights. But we should also mention the study's limitations, right? Every study has them.
Absolutely. Good science acknowledges its boundaries. They only looked at 5 lower limb muscles. A wider net might show more complexity. Also, it was only active young male adults. We can't automatically assume these exact results apply to women, older adults, less active people, or elite versus recreational athletes. More research needed there.
Yeah, different populations might respond differently.
And crucially, they tested one specific duration, 60 seconds cumulative. We don't know from this study what happens with, say, 15 seconds or 90 seconds. There might be a threshold effect.
Right. Those matters.
Which leads to a really interesting question to leave you, the listener, with. Given that 60 seconds cause these specific changes, the performance drop, the compensation, the timing shifts, how might different durations or intensities of static stretching tweak these complex neuromuscular control strategies? Could we potentially fine-tune stretching protocols based on duration to get different outcomes, maybe even beneficial ones in some contexts? Or tailor them much more precisely to individual needs in specific sports?
A lot to think about there. Finding that potential sweet spot, or maybe confirming that dynamic, is just better pre-explosion. Great question. Okay, so let's wrap up this deep dive. The key takeaway. 60 seconds of static stretching before a squat jump didn't change the number of muscle coordination patterns, but it significantly altered how and when muscles contributed, leading to lower jump height and that interesting compensatory effort. If this sparked your curiosity, definitely check out the full study. Again, it's 60-second static stretching of lower limb muscles disrupts muscular performance and control in active male adults by Guos and colleagues in the Journal of Sports Science and Medicine 2025. And hey, if you enjoy getting into the nitty-gritty of movement science and the latest research like this, make sure you follow our channel and hit those notifications. That way you won't miss our next deep dive. Thanks so much for joining us today on the Deep Dive.